The people leading the Vermont Bioenergy Initiative are forging the connection between diversified agriculture and renewable energy production. These farmers, scientists, and entrepreneurs are at the forefront of a local production for local use movement, and they are proving that local food systems and clean energy production together are economical, compatible, and essential. These are their stories. I'm Nataka White, Director of the Vermont Bioenergy Initiative, a program of the Vermont Sustainable Jobs Fund. With the help of a U.S. Department of Energy grant, we've been funding a number of algae to biofuels research projects in the state. Believe it or not, life on Earth depends on algae. Every day, algae produces more than half the oxygen on the planet while consuming vast amounts of heat-trapping CO2 during photosynthesis. These single-celled aquatic organisms convert sunlight, carbon dioxide, and nutrients such as nitrogen and phosphorus, into biomass and energy, and they do it very quickly, much faster than any plant that grows on land. The protein, carbohydrates, and oil, or lipids, that algae produce are what give it its commercial value. We're especially interested in those algae with high lipid content, because once extracted, these oils can be processed into renewable fuels, such as biodiesel. They also contain omega fatty acids and other nutritional elements, essential to human and animal health. The early stage research and development that's being supported by the Vermont Bioenergy Initiative is determining the most viable and cost-effective methods that will unleash algae's commercial potential to produce clean, renewable energy, treat wastewater, and supply nutrient-rich feeds and food.
I'm Sam Couture, and I'm an algae researcher. I got my start specifically looking at microalgae in grad school at the University of Vermont. Microalgae biomass has a lot of potential for different feedstocks for energy for our use. One of the ones that many people are focusing on currently are liquid biofuels from algae such as biodiesel. For microalgae to grow optimally, they need a few major inputs into the system. The major one is sunlight, another one is carbon dioxide, a third one is nutrients, so nitrogen and phosphorus sources, and the final one is water, the substrate in which the algae grow. As we learn more about microalgae, we're finding that high temperature can be a huge problem. But really the potential in the Northeast, we're finding that low light is great for oil production. Our overall yields could never compete with a very sunny place just because of the amount of sunlight in a given year. But if we're looking at co-products and oil per footprint per year, there's a real potential in the Northeast.
My name is Anju Thaya, President, General Systems Research. What we are doing is, first thing, looking for high lipid strains from the locally available algae and scaling those up to a level that it could be available for commercial use for production of algae, especially for biofuels. The native strains are expected to be highly adaptable to the local environments, and also we're looking at producing algae not just for biofuel but combining it with wastewater treatment. This is very significant because this would make the algae biomass production cost effective. This would also help in nutrient recovery, nitrogen, phosphorus.
I'm Jeff Marshall. I'm a professor at UVM in the School of Engineering, and I teach in fluid dynamics and particle flows. So we're working on mixing processes to maximize the growth rate of algae. If you stir algae, if you mix it and make the fluid turbulence, that the algae will grow faster. You can see a movement, as we show in the movie here, where the algae cells are constantly going up and down. Again, as they go down, they get darker and they have less light. As they go up, they have more light. So algae cells like a variety of light. So the question is, how much turbulence should we include to get the right amount of oscillation? And that's what's really exciting about what the Vermont Sustainable Jobs Fund is doing, is that they're investing into people who do different types of science and engineering and really trying to tackle the problem from the multidisciplinary aspect that's required for it.
My name's Sandy Worthman. I'm a co-founder along with Brian Holmes of Green Mountain Spark. We met while we were both pursuing PhDs in chemistry at UVM.
Traditionally, when people extract oils, there's a step that's called dewatering, where the water is separated from the algae cells. This has a huge energy input. What we'd like to do here is to extract the oil from the algae cells without having to separate the algae cells from the water first. That's the first goal. The second goal is to also convert that oil to green diesel biofuel. So we want to do it all in one step.
What we have here is the batch reactor. This helix is going to allow the algae to have a long resonance time in front of this lamp. There's a UV lamp that's down inside this cooling coil, and the algae will flow past that UV lamp, which will break and rupture the cells, releasing them in the presence of our reagents that will cause the fuel to be treated.
The ultimate end of this is to advance algae research by having a reaction system for biofuels conversion that improves the energetics of the system in general and makes algae as a biofuel source more viable.
We're really excited about this project with the Vermont Sustainable Jobs Fund because it could have a lot of relevance not only to algae oils but to any other vegetable oil feedstock, for brown grease treatments at wastewater treatment locations. We think that there's a tremendously broad utility to this technology.
I'm Josh Wilkenfeld, the Senior Algae Biologist for Carbon Harvest Energy. The vision of Carbon Harvest Energy is to take a waste product, which is methane gas coming off of landfills, and use that to power generators which produce energy. The energy can be put back into the grid and also be used secondhand to run aquaponic greenhouses, which include fish culture. The fish waste products are exactly the kind of nutrients that various plants require. So we'll be growing vegetables by cycling the water coming off of the fish into the hydroponic setup. Some of the wastewater from the fish will also be directed over to the algae. So the algae and the plants help clean the water so that that water can then go back into the fish. We're completely recycling everything, waste products, water, nutrients, turning all of that into a commercial product. One of the other things that algae requires is carbon dioxide. We're taking the carbon dioxide out of the exhaust gas of the generator, which serves as a key requirement of the algae itself, and at the same time helps reduce greenhouse gases. We're working with 3 different species of freshwater algae. There are other researchers in Vermont who are actually looking at various native species to try to see if any of those are going to work in this kind of system. There are 2 primary things that determine whether algae is going to be suitable for biomass production for either a food or a pharmaceutical or a biofuel product. Those key components really are the rate of growth by biomass production. And then the other thing is going to be, especially if you're interested in biofuel, is going to be the lipid content of the algae. The energy for algae comes entirely from the sun. In Vermont, we're dealing with a more light-limited situation. So we have to investigate the possibility of using artificial light and what the cost benefits would be in terms of growth of algae versus the additional electricity that we're going to be using. The Brattleboro project is meant to demonstrate all of the components and how they work together and give us a feel for scalability to try to get everything to fit the way that it's supposed to.
Algae needs to be part of Vermont's clean energy future, and here's why. As we study the available feedstocks, or the raw materials for renewable fuel production, algae stands out for its ability to produce abundant amounts of oil in a short period of time. Still, many challenges remain. And while it's true that algae farms in the Northeast can't produce the amount of oil that can be produced in a desert climate, what we are demonstrating is the importance of designing integrated systems. By locating algae production where waste nutrients and CO2 are readily available, and by concentrating on algae co-products as well as biofuel, these experiments and new patented technologies are showing that even small-scale facilities producing algae in the Northeast can make a viable contribution to the region's clean energy portfolio.